Welcome to the Math Record. Today we'll be covering convergence tests for infinite series. This video will be part 2 of chapter 4 in our calculus class. Okay, let's begin. So in our previous video, we introduced the concept of series as the sum of numbers in a sequence. Now the question is that sum approaching like some value? So in other terms, does this sum converge to like a numerical answer, or does this diverge? So usually we answer these questions using a series of convergence tests. So usually there's generally 5 convergence tests that you could use: the infinite geometric series, the integral test, the comparison test, the limit comparison test, and the ratio test. In this video, we'll be covering all 5. As a note, you only had to satisfy one of these convergence tests. So if you want to find out if a sequence converges or diverges, all you need to do is prove one of them. You don't have to prove all 5 for them to work. Okay, so let's move on to our first convergence test, which is the infinite geometric series. So what the infinite geometric series tells us is that if we take the sum from n, beginning with n, to infinity, because it's an infinite geometric series, so it's infinity on top all the time. For any of these convergence tests, it's infinity on the top. And if you take starting from n to infinity of a sequence that's in a geometric sequence, then if that ratio is less than 1, if the absolute value of that ratio is less than 1, then that sum converges to the first term divided by 1 minus the rate. So this might sound complicated, but it's easier when you see an example of it. So let's use a simple example. Let's say you want to find the sum of all the elements from x is equal to 1 to infinity from a sequence of 1/2, right? 1/2 to the power of x. So what would this sequence look like? Well, let's kind of put in some numbers first, right? So the first number is 1/2 to the power of 1, so it's just 1/2. The second number was when x is equal to 2, so 1/2 to the power of 2 is 1/4. The third number is when you put x is equal to 3, so 1/2 to the power of 3 is 1/8. The fourth is 1/2 to the power of 4, which is 1/16. And do you see this pattern? It's like 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, right? So the next one's 1/32, and then etc. and etc. and etc. Right? So this goes on for infinity. This infinity is on the top right here. So the question is, if we add all these numbers, 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus all the rest of the other numbers, what would that sum be? Well, what we could do is that we could use the idea of the infinite geometric series. So if it proves these conditions, that it's in the geometric sequence form and the ratio, the absolute value of that ratio is less than 1, then this is the sum. So let's see if it meets the condition first. Is this a geometric sequence? Well, it is, right? It's just 1/2 times the previous term, which makes sense because 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8. 1/8 times 1/2 is 1/16. So it's in a geometric sequence because the common ratio between uh, previous term to the next term is a actual common ratio. So what we could do now is, since we met the first condition, we could, does this meet the second condition, which is the absolute value of the ratio has to be less than 1? Or it's just telling you the ratio has to be between -1 and 1. So is it between -1 and 1? Well, 1/2 is between -1 and 1, so it meets the second condition. So since it meets both conditions, that means the sum converges to the first term divided by 1 minus the rate. So what's the first term? Well, it's just 1/2, right? So all you have to do is just have whatever the equation is raised to whatever you began with. Because it began with 1, you just raise to the power 1. So you have 1/2 1 minus the rate. The rate is 1/2. I mean, yes. Okay. So we will have 1/2. 1 minus 1/2 is 1/2. So 1/2 divided by 1/2 is 1. So the infinite geometric series convergence test tells us that 1/2 to the power of x, when you add all the terms as in it as a sequence, then the sum approaches 1. So the sum will become 1. Okay. Additionally, for example, this states absolute value of the ratio is less than 1 because the ratio could be negative. So let's say we have a summation from x is equal to 1 to infinity of, like, let's still use this simple case. Let's say negative 1/2 now, right? To the power of x. So its absolute value of r, that's 1/2. Is that less than 1? Well, it is, right? Since it's less than 1, that means this as a geometric sequence is going to be converging. So the first term is just negative 1/2 to the power of x. X is 1 because it began with 1. Divide by 1 minus the rate. The rate is negative 1/2. So you just have to follow the equation. So negative 1/2 to the power of 1 is negative 1/2. 1 minus negative 1/2, that's 3 over 2. So this would simplify to negative 1/3. So it's basically just that simple. All you need to do is that you have to make sure that that the equation is a geometric sequence, and the ratio is the absolute value of the ratio has to be less than 1. Or you could just say that the ratio has to be between negative 1 and 1. And that's basically it for the infinite geometric series. Okay, now let's move on to the next convergence test. This is the integral test. So it tells us that if we have a sequence, fn, right? If we have a sequence of fn, and it starts from 1 and it goes to infinity, if you add all those numbers in that sequence converges only if the integral from 1 to infinity converges. So instead of thinking it as a sequence, think of it as an actual equation. And if we put it from 1 to infinity, does that converge? So let's do this using an example. So let's say our equation, our sequence, is equal to 3n divided by 2n squared plus 1. Okay. So let's kind of list out some terms to see how this looks. So what's the first term? Well, that's when n is equal to 1. So that would be 3 over 3. Right? 2 times 1 squared is just 2, plus 1 is 3. So that 3 over 3 is just 1. Next term is when n is equal to 2. So 3 times 2 is 6. Divided by 2 times 2 squared is just 8. 8 plus 1 is 9. So this simplifies to 2 over 3. Okay. Now the next term is when n is equal to 3. So 3 times 3 is 9. 2 times 3 squared, 9 times 2 is 18. 18 plus 1 is 19. Okay. Now let's do one more. So n is equal to 4. So 3 times 4 is 12. And 2 times 4 squared, which is 32. 32 plus 1 is 33. So they're both divisible by 3, so that's 4 over 11. Okay. So looking at this sequence, we could tell that this number seems to be decreasing, right? Because that's 1. This is about 0.67. This one is roughly about 0.45-ish, I'm guessing. And this is roughly about 0.36. 36 or 37. ish. So you see that the number is decreasing over time. So does this tell us that this sequence 3n divided by 2n squared plus 1, does this converge? Well, what we do is that we use an integral test. So instead of saying the sequence from 1 to infinity, I only wrote 4 terms, but if you put an infinity, does that become like an actual number? Like if they add up, do they become an actual number that converges? So what we do is write an integral. So you have 1 to infinity of 3n divided by 2n squared plus 1. And you're doing it with respect to dn, right? So what's the integral of this? Well, let's use substitution. So u is equal to 2n squared plus 1. The derivative of u is equal to 4n, equal to 4n times dn in respect to dn, right? So it's times dn. So knowing this, we could substitute our integral 1 to infinity. So we already know 2n squared plus 1 is equal to u, because that's what we substituted with. And now we could substitute that 3n by this 4n, right? So to do that, we need to multiply the inside by 4 over 3. So 4 over 3 times 3n is equal to 4. So we will put that as 4n. But since we multiplied the inside by 3 over 4, right? We need to multiply the outside by 4 over 3. We need to multiply the outside by 3 over 4. Right? Because if this is 4/3 on the inside and this is 3/4 on the outside, then 3/4 times 4/3 is equal to 1. So we're keeping the equation the same, but we're just trying to scale this number up. So since this is 4n, and we have the dn from here, sorry, I forgot the 3/4 here, right? So the 4n times the dn, that is just du. So we could substitute this entire thing, 3/4 on the outside. That's 1, and that's du, right? So we're taking the integral of u in respect to du. It's just simple substitution for integrals, which we covered in chapter 3. So integral from 1 to infinity of 1 over u, and that 3/4 on the front is just equal to 3/4 of ln of absolute value of u. And our u is 2n squared plus 1. So let's substitute that back in. Absolute value of 2n squared plus. Let's make the absolute value bigger. So we have 2n squared plus 1 absolute value. And closing bracket. So since we had to take the integral from 1 to infinity, the first number is infinity, right? Well, the ending is infinity. So 2 times infinity squared plus 1 is just infinity, right? So it's just a really big number. So ln of infinity is just infinity. So the first number is infinity minus, you plug in 1. So 2 times 1 squared is 2. 2 plus 1 is 3. So ln of 3 times 3/4. Ln of 3, sorry. And then we have to scale that up by 3/4. So the integral from 1 to infinity of 3n divided by 2n squared plus 1, that is equal to 3/4 times parentheses infinity minus ln of 3. So this infinity tells us that it's just a really big number, right? So this equation is going to be increasing. So what this tells us is that since this is not a numerical answer, then this equation, 3n divided by 2n squared plus 1, as an integral would not converge. So this equation diverges. Since this equation diverges, then 3n divided by 2n squared plus 1 as a sequence and if you add all those sums up, then it becomes a series, that also diverges. So if the integral converges, then the sequence converge. If this integral diverges, then the sequence diverges. So it's going to be similar, right? So this equation diverges. So another way to tell is that instead of doing all this math and using this integral test, which you could use is a viable method, but if you want a simpler way, it's something you could use is called the P series. So P stands for polynomial. So what this series tells us is that if we have to take the sum of the elements of a sequence from 1, so n is equal to 1, to infinity of a sequence of 1 divided by x to the power of p, right? Which is why it's called the P series. Then if p is greater than 1, then this 1 divided by p, x to the power of p, this would converge. And if p is less than or equal to 1, but it's greater than 0, it's going to diverge. Okay, so that seems like a lot to unpack. So let's kind of understand how this works. So let's move this up. Let's kind of use an example to see how this works. So let's use our previous example, which was 3n divided by 2n squared plus 1, right? So what I usually do is that I look for the highest terms and only, well, the first thing I would do is to make sure they're both polynomials. So the top is 3n, right? So that's a polynomial. And the bottom is 2n squared plus 1, which is also a polynomial. So what I do now is that I just take the highest term from the top and the highest term from the bottom. The highest term on the top is 3n, and the highest term from the bottom is 2n squared. Right? So you take the one with the highest degree. So if you, instead, like if you add something else, like the denominator is added by 1/3 n to the power of 3, you change this to 1/3 n to the power of 3. So you take the term with the highest degree, basically. Okay. So when you have this, what you could do is simplify. So you divide n from the top and the bottom. So that becomes 3 all over 2n, right? And now you kind of just like think about this as the equation, right? So 3 divided by 2n. If you kind of like ignore the numbers here, this as a equation is just a simple 1 over n, which is just a reciprocal, right? So what is this as a power? Well, it's just to a power 1. So this tells us that p is equal to 1. So since p, the p, which is 1, since it's between 0, it's greater than 0, but it's less than or equal to 0, then this tells us that this equation, 3n divided by 2n squared plus 1 diverges. So instead of doing all that calculations with integrals, what you use is that if these are both polynomials, you could just use the P series. And that's the general idea of how you do it. But it is viable to use the integral test if you want to like prove it with an additional method. So let's try this with another example to see how this kind of works more. So let's say we have x squared plus 1. And the bottom is x 7 over 2 plus like x 3 plus 2. Okay. So what's the highest term on the top? That's x squared. What's the highest term on the bottom? That's x 7 to the power 2. Right? Because x to the power 3 is just 6 over 2, so 7 2 is bigger. So if you simplify this, it would just be 1 over x to the power of 3 over 2. Right? So this tells us that p is equal to 3 over 2. Since p, which is 3 over 2, is greater than the 1, that means this as a sequence would converge. So the general idea is that if you divide everything out and the denominator is between, and the exponent on the denominator, right, that 3 or 2 in this example, is between 0 and 1, and it's between 0 and 1, then it diverges. So the reason it has to be greater than 0 is because, like, let's say, let's delete all this first. Okay, so that's good. So the reason it has to be it has to be greater than 0 is that if it is less than 0, right? So let's say p is -2. If it's -2, so you have x divided by x, 1 divided by x to the power of -2. That's the same thing as x to the power 2, which is just a quadratic, right? If you could draw the graph of a quadratic, and you take the area under it, right? So if it goes to infinity, right? This area is always going to be increasing, right? Because the polynomial is always going up. So you have to add more area. So they're always going to diverge. So the reason it has to be between 0 and 1 is because then it kind of tells us that it's going to actually be in this form. We want it to be in this form. We don't want it to be a actual polynomial. We want it to be a rational function. So it's one like equation over the other. So we have like uh, x to the power of 5 over 2 plus 1, and we have like x on the bottom plus 2, we could automatically tell that this is not going to converge, right? Because x 5 over 2 is way bigger than x. So this top, if you plug in numbers, it's just going to get bigger over like a smaller number. So since this is always going to be bigger, the numerator, then this is going to tell us that it's always going to add more and more area. That means this as a sequence, the equation, that means this equation as a sequence, x to the power of 5 over 2 plus 1 divided by x squared plus 1, right? This will always be diverging, so it will never converge. But this equation, if you put it in a ratio, it might have a chance to be converging. But that's just a more explanation if you want to understand why these rules work. And that basically covers the integral test. Okay, now let's move on to our third convergence test, which is the comparison test. So the comparison test tells us is that we have a sequence a to the a of n, and we have another sequence of b to n, right? We have to compare this sequence because it says comparison test. If b of n, all the numbers of b of n respectively is greater than all the numbers of a of n, and a of n is all greater than 0, so they're all positive, then if b of n converge, then a of n also converge. Vice versa, always, because if b of n diverges, then a of n also diverges. So the idea is that if we have, let's say, a of x, and actually let's say b of x. Let's say b of x is 1/2, 1/4, 1/8, 1/16, and 1/16 and 1/32, right? So I'm just using a ratio 1/2, which we prove, which is just the sum of 1/2 to the power of x, which we proved to have a sum of 1 earlier on in the video. So we know that this converges. So let's say a of x is a ratio 1/3, right? So it's 1/3, 1/9, 1/27, 1/81, and 1 over 243, right? So 1/2 is greater than 1/3, 1/4 is greater than 1/9, 1/8 is greater than 1/27, 1/16 is greater than 1 over 81, and 132 is greater than 243, right? So that's be greater than each their respective counterpart in that sequence, right? So the first term of b of x is 1/2. The first term of a of x is 1/3. The second term of b of x is 1/4. The second term of a of x is 1/9. So you have to compare those respective numbers, right? So you can't compare the first term, like of b of x, to like the fifth term of a of x. You have to compare this one to this one, and you have to compare this one to this one. You have to compare this one to this one, right? So you have to compare them in order. And if all the numbers from one sequence respectively is greater than all the numbers of the other sequence, then it satisfies this condition, right? And if they're both sequences, then if b of x converge, then a of x converge. And we know b of x converge because that's just the summation of 1 over 2 to the power of n, right? So n is equal to 1 to infinity, right? So we know this converge because we proved this earlier in the video. So if this converge, then a of x also converge. And that's because of the comparison test. And that's the general idea for the comparison test. It does more logic than convention. So let's try to understand this more in another example. Okay. So let's say we have an equation 1 divided by n to the power of n, right? So we have these variables. So does this equation converge or does it diverge? So what we could do is that if we have, let's compare this to another equation. So usually when we have these kind of equations, you're gonna have to kind of logic your way through of it. So whatever you have on the bottom, right, n to the power of n, if n raised to the power of n is a big number, right? So generally, if you have 1 divided by a big number, then that number is gonna be equal to a small number, right? And you have 1 divided by a small number, you have a bigger number, which makes sense because you're dividing by a smaller amount of parts. So what we could do is that, oh, sorry, oops, yeah, example, 1 divided by n. So what we could do is that since it's n to the power of n, and the exponent is making this n like way bigger, then what we could do is that instead of substituting for the exponent, we could substitute for the base. So the comparison test takes a little bit more logic sometimes, which is why it's sometimes not used as much because it's harder to use. So we can substitute, like, let's say 2 to the power of n, right? So let's kind of like see if this makes sense. So 1 over n, its first term is 1 to the power 1, and 1 divided by that is just 1. Okay, so that sequence is 1. The second is 1 over 4, right? The third is 1 over ninth. The fourth is 1 over, actually, not 1 over ninth, is 1 over 27th. And the fourth is 1 divided by 4, which that 1 divided by 4 raised to the power 4. So that is 16 to 56. So it's 1 divided by 256, right, etc. So what is 2n? Its first term is 1 half. Its second term is 1 fourth. Its third term is 1 eighth. Its fourth term is 1 16th. And its fifth term is 1 over 32. Okay, so actually let's not have the 1 over 32 because I only have 4 terms on this one. So as you can see, is b of n, let's call this our b of n, and let's call this our a of n, right? Basically, whatever you want, whatever you're doing finding as a convergence or divergence, we want that to be a of n. Because if that equation is up here, it's not going to tell us anything. So we need to have whatever we have as what we want to find as converging or diverging, we have that as a of n, and this is b of n. So let's compare it. Is b of n always greater than a of n? So we have 1 half, 1. Okay, this fails. Let's look at this one. 1 fourth is that greater than or equal to 1 fourth? Well, it is, right? So these two are the same, which makes sense because it's greater than or equal to in this equation. Inequality. It's 1 eighth is greater than 1 27th. 1 16th is greater than 1 256. So the only thing that is less than is 1 half and 1. So since it's only one digit, it kind of doesn't really matter. So what this kind of tells us is that since 1 divided by 2 to the power of n is generally always bigger than 1 divided by n to the power of n, then this tells us that since this converge, then this also converge. So how do we know that this converge? Well, what does this look like? Well, it's just 1 to 1/2 to the power of n, right? Because if you kind of like distribute it out, it's just 1 to the power of n divided by 2 to the power of n. And 1 to the power of n is always 1. And 2 to the power of n is just 2 to the power of n, which is this equation, right? So since we already proved that 1/2 to the power of n earlier in the video converges, then since b of n converges, right? If b of n converges, then a of n converges. So since b of n converges, then a of n converges. And that's the idea of the comparison test, that you have to find another equation that's bigger. Well, each of the terms is generally bigger than whatever you're trying to find that converges or diverges, trying to answer, right? If the terms are generally bigger, then if the terms are also positive, because it's greater than 0, then if that equation that you find is um, if the equation that you find is converging, then the equation that you're trying to answer is also converging, and that's a general idea for the comparison test. So, about all the stuttering, right? Because comparison test still is a little tricky for everyone, including me. Comparison test is like as a advice, if you want to use it, it kind of takes a little bit more logic than you might are accustomed to. So if you don't understand how to use comparison test for now, um, the more you do of it, you could just get hang of it later. So that basically covers the third comparison test. I mean convergence test. Now let's move on to our fourth convergence test, which is the limit comparison test. So the limit comparison test is pretty similar to the comparison test. We have two sequences. A of n is our first sequence. B of n is our second sequence. A of x is the sum of all the digits, all our elements in our sequence in A of n. And B of x is the sum of the elements in the sequence B of n. Right? So it's the same thing as the comparison test. But now instead of comparing two equations, we're going to divide them. So we're going to divide the first sequence by the second sequence, and then we're going to take a limit of that. If the limit of that is a number, and that number is between 0 and infinity, then either both the sequence converges or both of them diverges. So let's try to understand this using an example. Right? So let's use something simple. Let's say we have infinite summation as n is 1. Sorry, n is equals to 1, and it goes to infinity. And we have x divided by x to the power of 7 divided by 2. Sorry about that. Plus a 1. Right? So what we have to do first is that since we only have one sequence, we need to get another one. So our next sequence is what you could do is that we could like think about this in a limit, right? Because it's a limit comparison test. So what's the general equation if we take the limit of this? Well, the general equation is just 7x divided by x to the power of 7 over 2, right? We could ignore the 1 because if x becomes a really big number, right, as you take the limit of it, as it becomes a really big number, then the only thing that matters is on the bottom it's x to the power of 7 over 2, because this is going to become a big number, and 1 is such a small number, it's not going to matter. So we have x divided by x raised to the power of 7 over 2. That simplifies to 1 over x to the power of 5 over 2. Okay, so this is going to become our b of n, right? So that's going to become our second equation. And this is becoming our first equation. This is our a of n. So let's kind of substitute it into this inequality. Right, so delete this, and I'll rewrite b of n. So our b of n is equal to 1 over x to the power of 5 over 2. Okay? So what do we know about this equation? Well, if we use the idea of the p-series, which we covered earlier in the video, we know that if p is greater than 1, it's going to converge. Well, what's the p here? The p is 5 divided by 2. Since 5 over 2 is greater than 1, then this thing converge. Okay, so we know that b converges. So B converge. Okay. So let's have A of n divided by B of n. So A of n is just x. We need to take the limit of that. So the limit as n approaches infinity of A of n divided by B of n. So it's just A divided by 7 over 7 divided by 2 plus 1. So that's A divided by B, which is 1 divided by 5 over 2, which is basically just multiplying by 5 over 2, right? So what does this multiply to? X times x to the power of 5 over 2. Well, this simplifies just to x to the power of 7 over 2, right? Which is the same power as this. So as you take the limit of that, you just have to divide the coefficients. So the coefficient of this one, of the numerator, is 1. The coefficient of this one is denominator is 1. So 1 divided by 1 is 1. So the limit is 1, right? So since 1 is between 0 and infinity, this tells us that either both of the equation converges or both of them diverges. So how do we know which one it is? Which one it is? Well, we already know that B of n converges, right? Because we use the P series. So since B of n converges, that means A of n, which is the one that we're looking for, also converges. So it might seem confusing, but the more you do of the limit comparison test, the easier it gets. Similar to like how it works with just the comparison test. So usually the comparison test takes a little bit more logic and theoretical sense than actual than the actual other tests. So if you wanna like spend more time on the limit comparison test and the comparison test, it would probably make more sense. It takes a while to understand. And that completes the fourth convergence test. Now let's move to our final convergence test, which is the ratio test. So the ratio test is probably the one you most likely want to use. It's not always convenient to use this test, but it's usually the most fun, I guess, in a way. So the ratio test states that if we have a sequence, which is f of n, right, and it goes from 1 to infinity, and if you take the limit of the next term divided by the previous term, and you take the absolute value of that, you get a positive number or 0, right? And if you have this number, this constant c, if this c is less than 1, it's converging. If it's equal to 1, we don't know what it does. And if it's greater than 1, it diverges. So let's kind of understand this using an example, right? So usually when you use this ratio test, you either are dealing with factorials or you're dealing with exponents. If you ever see a factorial, you usually would use the ratio test, which is the most likely to use, which I'll explain later using using this example. So let's say we have our sequence is 2 to the power of, let's say 2 to the power of n divided by n factorial. Does this sequence converge or does this diverge? Well, what we could do is that we could use the ratio test. So we could do the limit as n approaches infinity of absolute value of the next term divided by the previous term. So the next term in general is that you could just add 1. So you substitute n with n plus 1. So you have 2n plus 1 divided by n plus 1 on the bottom, factorial. And all this is divided by f of n, or f of n is 2n divided by n squared, okay, and factorial, right? So you take the absolute value of this entire thing, and that will give us c, right? So let's kind of simplify this first. So let's kind of rewrite this. So this is equal to 2n plus 1 on the top divided by n plus 1, oops, sorry, n plus 1 factorial on the bottom times, right? Dividing by a number is the same as multiplying by its reciprocal. So that's multiplying by n factorial over 2n, right? So this simplifies out too. So 2n plus 1 divided by 2n is just a 2 on the top, right? Because this 2n plus 1 is the same thing as 2n times 2, a power of 1, right? So you cancel out the n, cancel out the n here, you just had that 2. And that's why this is 2, right? And that's the reason why we could use this with exponents, because it kind of factors out pretty well. And now we have factorials. So the reason we could use these with factorials is that it does the same thing. It can factor things out. So we have n factorial. If you could divide this by n plus 1 factorial divided by n factorial, it's just n plus 1 on the bottom. So it's a little messy, but the idea is like, let's say instead of n factorial, it was 5 factorial, right? So if this is 5 factorial, then this is 6 factorial. This is because this is n factorial on the top, and this is n plus 1 factorial on the bottom, right? So 5 factorial divided by 6 factorial. And we're left with 6, right? Because n plus 1 is what we're left. So we plug in 5 here, that's 6. So the reason we could just leave a 6 on the bottom is because 5 factorial is just 5 times 4 times 3 times 2, right? And 6 factorial is just 6 times 5 times 4 times 3 times 2. Cancel out the 2's, cancel out the 3's, cancel out the 4, cancel out the 5. What do we have left? The 6. And that's the reason why we could just use factorials, because we could use factorials for the ratio test, because it factors out like really well. So all this simplifies down to is just the 2 on the top and the n plus 1 on the bottom, right? So this we could just substitute back. Let's delete all this. So this is just 2. So 2n plus 1. Okay. Let's kind of delete all this first. So we had to take the limit as n approaches infinity, absolute value. All that factors out to 2n plus 1, right? So what does this equal to? As n approaches infinity, the denominator gets really big. So 2, which is a small number, divided by a really big number, is just a really small number. So a really small number, that's 0, right? So c is equal to 0. So now we just have to look at this list, right? So where does that go? Well, it goes in the first one, right? Since c is 0, 0 is less than 1, then it converges. And that's all we need to know. Then that's all we need to do. So that tells us that since the limit as 2 divided absolute value of 2 divided by n plus 1 is equal to 0, that means this equation converges. So, and that's the basic idea of using the ratio test. Overall, this entire video, we just covered the 5 convergence tests, which is the infinite geometric series, which is what you could only use for geometric sequences. The integral test, which is what we could use when we're dealing with equations that we could take an integral of. The comparison test and the limit comparison test is when we have two sequences that we could compare to each other, but that takes a little bit more logic. And the ratio test, which is what you use when you have factorials or like exponents. Well, thanks for watching, and I'll see you at the next math record.